Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we have a further look at tree diagrams. Now, in this video, we'll look at using tree diagrams when the multi-stage event that we're interested in is neither with nor without replacement. So that happens when each stage is like a different event. So this is the kind of question for which we would use it. So let's say the probability I obtain an A in maths is 0.75. In English, it's 0.6. What's the probability I obtain an A in one, but not both subjects? So remember, the whole point of a tree diagram is to list all of the possible outcomes in a neat way that makes it a bit easier to understand. So here we have two stages. So the first stage is going to be whether or not we get an A in maths. So I'll just call it A and not A. This refers to maths. So the probability I get an A is 0.75. Probability I don't get an A would be 0.25. So the second stage will be describing English. So I could get an A in English or not an A. An A or not an A. So the probability I get an A in English, I'm told, is 0.6. So the probability I don't is 0.4. So this is what my tree diagram will look like. So once again, I'll go through and write the outcomes. That's kind of the point of doing this. So I could get an A in both subjects. This means A in maths but not English. An A in English but not maths, and an A in neither. So remember to calculate the probability of each of these events here. I can't just say they're all a quarter. I go through and multiply the branches. So the probability of getting an A in both is 0.75 times 0.6. So here, the probability I get an A in maths but not English is 0.75 times 0.4, which gives me 0.3. The probability of getting in English but not maths, 0.25 times 0.6, which is actually 0.15. And then the last one, 0.25 times 0.4 gives me 0.1. So when we get the probabilities of all of the outcomes, they should add to 1, otherwise I've done something wrong. So remember, when we were doing with or without replacement, these ones would have been the same. If you had, one A and one not A, the probabilities would have been the same. But that's not the case here, because it's not with replacement, it's not without replacement. So the probability I obtain an A in one, but not both subjects. So this 0.1 doesn't count. I'm only counting these two here in green. These are the two events where I got an A in one, but not both subjects. So the probability that this or this happens, of course, I just add them up, and I get 0.45. So that is the answer to the question. Probability I get an A in one, but not both subjects, is 0.45. Let's look at an example that's slightly harder now. So let's look at this question here. So Daniel plays 3 sets of tennis. Probability he wins the first set is 0.6. If he wins a set, the probability that he wins the next set is 0.8. If he loses a set, the probability he wins the next set is only 0.3. We're going to find the probability he wins at least 2 sets. So we're going to use a tree diagram here. Remember, the point of that is to list all the possible outcomes. So we're talking about 3 sets of tennis. So here there are 3 stages. So at each stage, he could win or not win, i.e. lose. So win, not win. I'm sure you know how to set this up. So our tree diagram looks like this, and then let's write all of the outcomes. So there should be 2 times 2 times 2, i.e. 8 outcomes. So here are all the 8 outcomes listed here. So this is why tree diagrams are useful. We can see all of the possibilities, and we can just count which of these results in him winning the match, which is winning at least 2 sets. So this is him winning at least 2 sets, so we'll circle this one here. This next one as well, he wins 2 sets, wins at least 2 sets there, and then this one here. Okay, so that's the handy thing about the tree diagram. It shows us all the ways that he could win at least 2 sets. So now we just have to find the probability of each of these. And no, each of them doesn't have probability 1/8 because they're not equally likely. This is a bit complicated because the win and not win probabilities change all the time. So let's go through and look at what the question's saying. It said the probability he wins the first set is 0.6. So that's obviously 0.6 and 0.4. Now it says if he wins a set, that is, the probability he wins the next set is 0.8 because he's grown in confidence. So this will be 0.8 and this will be 0.2. So if he's won this second set, the probability he wins the third set will again be 0.8. If he wins a set, the probability he wins the next one is 0.8. Probability he loses is 0.2. But if he loses a set, the probability he wins the next set is only 0.3. So the probability he loses is 0.7. So similarly, if he loses the first set, the probability he wins the next is only 0.3. And then 0.7. Now, he's won here. This is saying if he wins the second set, probability he wins the next set is 0.8 because he grows in confidence. And the probability that he loses that will be 0.2. Here he's lost the second set, so the probability he wins the next game is only 0.3, and probability he loses is 0.7. That's sort of the hard part here. That's what makes this tricky, that the probabilities are always changing. They're not changing in a predictable way like when it was with or without replacement. Okay, so now we can find the probability of each of these outcomes. So the probability he wins all three sets is 0.6 times 0.8 times 0.8. So if we put that on the calculator, we should get 0.384. So that's the probability that he wins all three. So then the probability he wins the first two but loses the third, 0.6 times 0.8 times 0.2. And that gives us 0.096. So as I showed you in the previous example, see these here that have all of the same number of wins. So these three here have 2 wins and 1 loss. Now, when we were doing with or without replacement, all of these had the same probability. But this time we see they're not going to have the same probability. So the probability he wins, then loses, then wins again is 0.6 times 0.2 times 0.3. So that's only 0.036. So we didn't get the same probability for these two, which we always would get if it was with or without replacement. So the last one I need to calculate is this one here. So that's he loses, then he wins the next two sets. So 0.4 times 0.3 times 0.8. So this one here gives us 0.096. So that's just a coincidence that these two were the same. You can't assume that the same number of wins means the same probability here as it was the case with or without replacement questions. So to find the probability that he wins at least 2, we just need to add up these probabilities because we're saying what's the probability this or this or this or this happens. So all we need to do is add up these 4 numbers. So adding all these up in the calculator gives us total answer of 0.612. That's the probability he wins at least 2 sets. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.